Welcome to today's Postgres conference webinar, OpenStreetMap to PostGIS Easier and Better. We're joined by Ryan Lambert, CEO at Rustproof Labs, who will live demo how easy it is to import high-quality OpenStreetMap data into PostGIS and Postgres. My name is Lindsay Hooper. I'm one of the Postgres conference organizers, and I'll be your moderator for today's webinar. A little bit about your speaker. Ryan started his technology-heavy career in 2003, working in the professional audio industry from a computing perspective. By 2008, he had become fully immersed in the world of databases, programming and automating away tedious data-related tasks for the office. PostGIS was the driving force behind his initial use and eventual love of Postgres. With that, I'm going to hand it off to Ryan. Take it away.
Thank you, Lindsay, for that introduction, and thank you to PostgresConf for hosting yet another webinar of mine on PostGIS and OpenStreetMap. We're going to get started. I'm going to point you at our website that has some downloads for today. It's great to be able to follow along. You can just go to blog.rustprooflabs.com right now, and it'll be at the top since it was the last thing published. There are two links. There's a shell script and a SQL script that you can download so you can follow along. I do my best to make sure you can read the text on my screen, but it's easier to be able to navigate and scroll on your own time. If it's easier for you to find the PostgresConf website where you registered for this, the link is also down there under session downloads to get back to those files. So having these files will be very handy today as we're going through the session, and later, since the session will be recorded, you'll be able to follow along and run this code on your own time. So today, it's all about live demo. We're going to start out with loading OpenStreetMap data. That is covered in the shell script you can download. And then there's the rest of it will be over the SQL data, SQL queries that we have accumulated. As Lindsay said, please ask questions in the chat throughout. I'll take a few breaks here and there to field them as they come through. And I do have a few slides, but I promise it's a very small number of slides, with the majority of it being the actual demo. So the project I'm working with is called PgOSM-Flex. This is essentially a wrapper around OSM to PGSQL's Flex output. I started playing around with the Flex output back in December of 2020, and in the last few months, I've completely abandoned the legacy import and am only using this new Flex import via the PgOSM-Flex project. It has a collection of Lua scripts that are the styles for OSM to PGSQL, and then there's a collection of SQL scripts that handle the post-processing cleanup that does a whole bunch of stuff that isn't really appropriate to put in for OSM to PGSQL to handle itself. The goal of all of this is high quality data geared towards analysis. I've outlined a number of my opinions on what I think high quality data are. There's a blog post linked here that I pulled these from. These basic opinions are also iterated on the GitHub page with the project. But I believe that we should follow some database best practices. Primary key and not null are both good things. All supported versions of Postgres now support JSON and JSONB. So I'm also taking this as an opportunity to get rid of my use of HStore. And then I want my units in meters or kilometers per hour in a way that I can actually use them in aggregate queries and know that they're going to be the same units throughout the database so I can do a proper analysis. The other part of PgOSM-Flex is the Docker image. This is part of what makes it really easy to get started and experiment. I build the Docker image off of the PostGIS image, which is ultimately based on the Postgres image. And then I bake in some OSM to PGSQL stuff, get all of that installed and load in the PgOSM-Flex, and that does all the rest of the magic. The latest image is always following the main branch in the repo. And the latest image and tagged versions are also all available on Docker Hub. This Docker image is really geared to small regions. The break point is around 1 gigabyte of a PBF file. As you get bigger than that, it may be worthwhile to look into installing the software on a server and configuring it for your specific needs. the Docker image contains Postgres vanilla defaults, and it is not optimal in any way, shape, or form. The OSM to PGSQL documentation on their website has some guidelines on how to configure Postgres, but that is beyond the scope of today's talk. So we're going to jump into the first part of the demo, and this is going to be the shell script that is available for download. And I have the same script open here just so I can look at it and copy and paste. The first thing I'm going to do is copy my stop and remove commands. I want to make sure that there's not an image running container in the way when I go to run the image. The next is to run the start your container up. Oop. Had the wrong clipboard there. This starts an image called PgOSM. You can see that it's here, and it's running on with Postgres exposed on port 5433. I do this because I also have Postgres running on the server itself, and it is using the default of 5432. So I just moved that Docker image out of the way, or the Docker container out of the way, to not conflict with the base Postgres installation. Then the Docker exec command handles all of the magic of getting your data ready. I'm going to go ahead and just kick this off. When you start running it, it'll tell you that there's a log file based on a shared volume that's set up with a container that we can monitor progress. And that window has frozen, so I won't show you that. Oh, there it goes. It was waiting for a while. And it goes through some output. There's some OSM to PGSQL output in this log file. And it's already into processing ways of the District of Columbia. It's a nice small region, so it processes pretty fast. If you've ever ran OSM to PGSQL, this step right here should look fairly familiar. While that's running, we're going to come back here and just look at this command a little bit. When I ran the container to start with, I set up this volume under this PgOSM data folder. That allows me to access the PBF files and the output file that it generates. The exec command handles setting some environment variables. In this case, I'm setting the target schema to end up with under OSM_DC. This is because I'm loading the District of Columbia, and it renames it from the default of OSM to allow me to import multiple regions into the same target database, each region in its own schema. This line just tells it to run the shell script that's baked into the Docker image. These two parameters are passed in. These are used to download the file from GeoFabric. So this has to match up with the region and the subregion in the URL of the GeoFabric download file. 2000, this allows us to set the cache for OSM to PGSQL while it runs for the nodes. And then run all is this is the layer set in PgOSM-Flex. This is determining which layers of all of the layers do I want to load. And while we're in here, I'm going to look through these other commands. I'm not going to run these during today's demo. They just take too long to get through in the short hour we have together. But I run Colorado into OSM_CO. Again, it uses the run all layer set. And the next one runs Colorado again. This time it uses a 2 at the end of the schema name to separate it from the first one. And this runs a table called unitable that we'll look at the very end. And then the last Docker command I have here loads the US West subregion. Now this region is bigger than the 1 gigabyte I said to kind of limit yourself to with this Docker image. And if you run this Docker image versus installing it and tuning it on a server, you'll notice that the Docker image is quite a bit slower. So there are some optimizations that could be done there. After the Docker commands have all ran, I create a PgOSM database on my local machine. That's the Postgres at 5432. Install PostGIS, and then I run a few PSQL commands. These just pull data from that shared volume, PgOSM data, and it runs this SQL script. This is the output from running that Docker exec. When it gets done processing the data and post-processing the data, it uses pgdump to spit out a SQL file that you can load into whatever servers you want. So back at the terminal, I can see here, we have some comments up here. This is from the post-processing SQL scripts that creates comments to alters table, creates index. And then it lets us know that it's done and it spit out a SQL file. In the window where I actually ran the Docker command, it tells us that if you followed the README, there's a file right here that you, this is where the SQL file is. So if I just load this up in Nano text editor, we can see at the top, it looks like if you've ever ran pgdump, this is pgdump. And the first thing it does after those set commands is it creates that OSM-DC schema that we told Docker to use. So we have a data file here, and if instead of looking at it, I can do an ls, and we can see that this one file is 142 megabytes. So we downloaded District of Columbia. It's like a 17 megabyte PDF, and it spits out a 142 megabyte SQL script that we can load into SQL. So with that, we're going to jump back to slides for just a little bit longer. So when we ran the Docker exec, it triggers this shell script that's part of the Flex repo that gets baked into the image. It downloads the files from GeoFabric, as the first bullet point says, and that ties in with the last bullet point. It archives the OSM PBF and MD5 files with the date that it was ran. So if you have a tendency to keep around files so you can rerun analysis, this process will help you auto-archive it. And in the future, if you want to re-import this, you can, it'll handle the date as an environment variable at runtime, and it'll allow you to import a historic data file that you save down. So that's something I do on a somewhat regular basis, and so I bake that into part of the core functionality. There are currently 4 layer sets defined in the Flex project. There's the run all, and that runs pretty much everything. There's a couple things it doesn't include, but it runs everything that I find to be useful. Run no tags is basically the same as run all, but it leaves out the tags table. And so by doing that, you skip the JSON-B entirely. And then if you're looking for a minimized data set, there's the road place layer set that only imports roads and places. And then the unit table just loads everything into one giant table. It's not intended for any sort of production use, but it's very helpful for debugging and finding why a particular element might not have shown up in a layer that you expected it to. So these layer sets are pretty simple. They just require other files. The Lua scripts are the styles that work with OSM to PgSQL-Flex. And then the SQL scripts are post-processing scripts to create constraints, indexes, comments, all that good stuff. So how do we customize this? What's the magic that makes all this work? And this is really tying in with the OSM to PgSQL-Flex project. All I'm doing is wrapping around that with these Lua scripts and post-processing SQL. So in the style folder, there's a bunch of Lua scripts that are succinctly named to indicate what is in that layer. We have indoor, we have building, we have land use, places, road, all sorts of styles are in here. I'm going to take a peek at place.lua. This is one of the ones that I find is more interesting than some of the others. And all of these styles are going to start out by requiring the helper script. And we'll go over what's in that helper script here in just a little bit. But in here, we use the OSM to PgSQL constructs to define tables. They actually let us create tables with structures that we want. We get to define the columns, what we want the columns to be named, what data type we want, and would you like it to be not null? Sure, thank you, I would like that. So we have a lot of option here to customize how our tables are structured in Postgres, instead of just getting your planet, point, line, and polygon tables. And so this place layer, it has a point, there's a line, and there's a polygon. So we're going to create 3 tables for places, one for each major type of geometry. And then we get into the processing. There's a function here that processes the nodes. I'm going to scroll past this one and down to the function that processes ways. The node processing and way processing are almost the same, but ways actually include 2 types. Line and polygon are both considered way. So we get handle both of them here. The first thing that one of these processing functions do is they determine what to even look at. So here's how we say, what are places? Well, they have a tag of place, they have a tag of boundary, or they have a tag of admin level. If they have any one of those 3, they get considered as part of the place layer. Then we can define columns. So I'm grabbing the OSM type column. Here I'm actually grabbing the value from the place tag. But on the other 2, I'm not actually grabbing their details from boundary and admin level. I have dedicated columns in the table for those, as we see down here. So I'm just setting the OSM type to those categories instead of getting a detail. And then here's where we did have a switch to handle polygons versus lines. Hey, is this object closed? If it is, we're going to call it a polygon and put it in that table. If it's a line, we're going to put it in the line table and create a line versus creating an area. So this is the portion of the project that interacts directly with OSM to PGSQL that allows us to customize the data, clean the data, and improve the data as it comes into the database versus waiting for it to be in the database and then trying to clean it up after the fact. Now on to the SQL side of things. The SQL folder has the same set of layer names, amenity, building, indoor, infrastructure, that the Lewis side had. These are just now SQL scripts. If we look at the place.sql, the first thing here are comments. We're commenting objects. We're describing what our data has, what our database is storing. This is a key element to high quality data. If you don't know what your data is, what it means, and where it comes from, do you know what data you have? So this is a good helping tool to help users that are in the database. They can see these comments from in the database, and wherever possible, I'm trying to link to the OSM wiki itself for, hey, why did Ryan decide to do this? Well, I hopefully read the wiki and implemented what was described and community accepted. I'm really trying hard to focus on adhering to the community standard wherever possible. And then we add primary keys. OSM ID is a primary key in all of these tables. You can count on only having one OSM ID in the road table that matches up to that line instead of having those split by default. We create some indexes, help query performance for some common performance patterns, querying patterns. We can create views. There's a view here. There's a materialized view here. More comments. Now we're creating a new table. So there's a whole lot of post-processing that goes in. This whole script is 270 lines of SQL on the place layers after it finishes with OSM to PGSQL. So all of the customization that I'm doing is either inside of those styled Lewis scripts or it's in the post-processing SQL script. The helpers script, all of the independent layers will bring in this helpers script. And one of the reasons is this is where we're handling environment variables. So I personally am using 3857 as the default for my project. So I made that the default. But if you want to use 4326, you can pass in PgOSM_SRID as an environment variable, and it'll use that instead of 3857. There's, I think, 5 or 6 different variables that are handled here inside of the helper script. The other side of the helper script are functions to clean the data. Get name is one of my favorites. This looks at multiple name columns from the various tags in OpenStreetMap. There's name, then there's alt name and short name and local name. So there's all these different name columns and they're not filled in consistently as you look around different regions of the globe. So as the data is coming in, this get name function in the helper script does an okay job of trying to make sure you have at least one name to work with, and you don't have to write a bunch of wacky SQL code in order to get to a name for that one polygon that's missing it. Another, getting into consistent units. There's a function that returns whatever data is in that column as meters. Same thing with parse speed. It gets your unit in kilometers per hour. Again, we're matching the OSM defaults, not our defaults. I'm in the US. I don't think in kilometers per hour, but I want my data to be consistent. And then we have some other functions that grab other various indicators that we'll look at in the SQL code. All right, so there are 4 schemas that shell script will create in the target database. And I have all 4 of these loaded in a demo database we're going to go query now. Most of the examples I'm showing either use OSM-CO or OSM-US West. So that's where we'll be spending the rest of our time for today. We are on to the demo on the SQL. It looks like I have a question that came through. Curious about the interaction with various languages, thought about this with the get name. So I'm not doing anything specific to handle language specifics. There is a way in Lua to grab tags based on part of the tag's name. And I think what would need to happen there is to look for, I think it's like name : EN for English, or name : UK for UK English, if I'm understanding your correct question properly. I currently am not doing anything with that, but that would be a really, really handy addition to add in. And one thing I'm going to do after this recording is posted is I'm going to rewatch this recording and make notes of all these things that I say, well, that would be nice. And I'll work on adding them as issues in the GitHub repo so we can actually track them and make improvements here. Yes, it is global and it's a fantastic project. And so I was so happy to see this Flex output. To dump everything I had been doing and just give it up for a new format did not come lightly. But this is the kind of improvement with these name handlings that we can actually make them for the community, and not just make it, well, I wrote this code in my database. That isn't as shareable as something like these Lua scripts are. All right, so we are in the database. I am connected. If you have downloaded the SQL script, this is the very same code that I'm looking at. This first query, nothing really exciting, but it's metadata. Data about our data. And one of the things I'm most happy to have in here is the date that the data was loaded. I don't know how many times I've come back to something and go, oh, this has been at least 2 or 3 months, but when was it actually loaded? Is it old enough to justify a refresh, or is it still recent enough that I can use it? So as you import it, it will track the date for you, which is really handy. The other 2 pieces that are really handy is knowing what version of PgOSM-Flex you used, because as we make improvements to this process, in this project, your data is going to be different based on what version you used. And the same goes with the OSM to PGSQL version. It grabs that and tracks that along with it as it's running and puts it into this PgOSM-Flex table. So every schema that has been loaded this way will have this meta table with the Flex. This particular query is joined to my data dictionary extension. And the reason I threw that in here is just to kind of get an idea of how many tables and the size of the data. So the Colorado one is this first row. It is just under 2 gigabytes the way I loaded it. US West, which I only loaded roads and places instead of using run all, is 3.3 gigabytes. And we can see the difference here in the table count. We only have 7 tables versus 35. To give an idea of how the data grows over time, or over region. Going into some actual OpenStreetMap data now. This query, it does a join just so I can filter it down to a reasonable area. We're looking at the data from the road line table. Of all of the OpenStreetMap data, I think I use the road line data hands down the most. It was the first layer it was the reason I started using OSM was getting roads data for display. And I always find reasons to use the roads from OSM. So we have some columns that look fairly typical for a road layer. We have max speed. And if I hover over here in dbeaver, it's going to display the comment on that column. So in that post-processing SQL, we had all those comments. They're visible to the end user right here in the GUI if you're using something like dbeaver. And this will tell us that it's in kilometers per hour. It has a link to the OSM wiki, so you can get to why I chose km kilometers per hour. And I see I have a typo in there. It says km over kr, which is not correct. I will fix that as well. But so those comments are a big part of understanding what's actually in here. There are a few handy indicators we're going to spend some time looking at. One is a major indicator. This is a Boolean, true, false. Is this a major road? And then the same goes for these route underscore. Is this routable via foot or bicycle or motorway? As some Boolean indicators that we can query on easily. Using the OSM US West schema, I had this one it will take a few seconds to run while it crunches all these aggregates. The first two columns are a row count and a distinct OSM ID. This is just to prove that in all of this data I've loaded, there really is only one OSM ID per row. We do not have duplicates that we have to fight later on if you're doing some sort of analysis. Looking at this, we have 7.7 million roads. And of those 7.7 million, 770,000 of them are considered a major road. So a very small percentage of them are actually the major roads. And that's one of those layers I use all the time. I'm always filtering down for major roads. And then these routing indicators, just to give an idea of how many different road segments are routable via motorway or footway or whatever. So on the topic of major roads, I ran this with explain analyze. So we can kind of get an idea. One, I want to make sure it's using an index. But this is a very common kind of query that I would run where I'm saying, hey, I need this list of highway tags because I want all of these major roads. The first gripe I have about this is an easy query to get wrong. If someone accidentally deleted secondary link, how easy is it to spot that difference? It's really, really hard, especially if someone had deleted all the line breaks and this was all one giant line of this, finding the missing item out of 10 items is not necessarily easy. It is using an index, which is that's good for performance, but it's not as good of an index strategy as this is. And this is also much, much, much easier to read, write, and make sure that I don't get it wrong. I'm always just saying, hey, get me the major roads. And this one runs in about 600 milliseconds or a little bit less. The other one runs in about 700 milliseconds or so. It's a little bit slower. The other thing with this more complicated looking query is the query plan is more complicated. It starts by doing a bitmap index scan and then has to follow it up with a recheck and a heap scan. Versus this one, it's purely an index scan. So even from looking at it from a planner perspective, it's less complex. It's also easier, and you don't have to think about what's going on here. And just to kind of give an idea of what this looks like in the Lua script, back to the browser. All it's doing, this is the same filter that I had on that first query. It just handles it all for us in the pre-processing steps. So we don't have to think about it at runtime. You don't have to have analysts writing SQL code thinking about what are major roads. It's just codified as part of the project. This is the kind of query. So here we're using route cycle and route foot to say, I want to find all the places I can ride my bike, but I probably shouldn't be walking there. This kind of query would be extremely difficult to write in the legacy format, just using all the tags, as it has to use a multitude of tags, and these combine in an and or style in SQL, which are A, complex and hard to write, and B, error prone and hard to troubleshoot. So this is the kind of benefit that we can get directly in SQL without having to write complex SQL that's hard to troubleshoot later. I can run this here, and I'm going to run it again with explain. It's not the fastest query. I haven't indexed either of these columns because I don't think everybody's going to be using them. It wasn't worth creating an index by default. But even without an index, it's returning 500,000 rows out of 7.7 million in 2.5 seconds. That's really not bad. And the analyst didn't have to spend any brain cycles trying to think, okay, now how am I going to codify cycle routes but not footway routes? So that kind of logic gets kind of messy and tricky using that unstructured tag data directly in SQL. Let's see, I'm looking for any questions. I don't see any new questions. If you have them, please go ahead and type them into the chat. And so moving on to places. Places are the other thing I just use a lot. I have written a blog post that kind of goes into some of the other improvements that I've made to places. That link is available here from this SQL script. One of the challenges I've dealt with is duplication between relations and their member parts. This is a huge pain and has caused me many, many hours of painful deduplication and figuring out why my analysis went wrong. If I'm trying to do a tree count of how many trees there are in Golden, and it gives me double the expected number, you have to go and find where that duplication happened and get rid of it. And there's all sorts of manual, ad hoc, hacky sort of ways to work around this, but it's always a kind of a pain in the butt. And what we have is the ID that has a negative number is a relation in OpenStreetMap, and the ID with a positive number is a normal polygon, multi-polygon that is part of that relation. What I did in the Lua script for places is we load in the member ID data. And so this allows us to link this first ID here matches this one here. Now, the astute observer may be like, hey, but why are there two IDs, but they're not three lines here? Where's the 3311, 3235? Well, that's either a line or a point. And so if I had brought in the line or point table to this, it would also have that represented there. Relations in OpenStreetMap are complex beasts, and they can act kind of strange at times. But this is duplication. This is a problem. I don't like this. There's a view, vPlace polygon, instead of just the table place polygon. It only returns one row for Golden. It goes through and removes the duplicating member polygons. So when you are doing a join between this place polygon and that other feature layer, it doesn't just duplicate a whole bunch of rows because there's the duplication in the polygon layer. How big of a problem is it? That's noticeable. I think this is like 23% of all of the polygons are duplicating an actual relation. So this is looking at US West. The full data set has over 26,000 rows, and about 6,000 of those rows get removed as duplicates. So that's a very significant amount of duplication that you don't have to fight at runtime now. All right. So large polygons. This is where a lot of users of PostGIS run into performance problems. When you're working on, you have a large polygon layer, which our admin boundaries are large polygons by definition, and you are joining to another layer. In this case, I'm joining the place layer to the road layer. I'm using an st-intersects to say, give me all the roads that intersect with all the places of admin level 6. In the US, this lines up to be our county level data. If I'll run just this query by itself to start with. And just take one second. There we go. Get an idea of what the data looks like. It only returns 68 rows. There are 68 level 6 polygons in Colorado, and we get a count by each one of those. Nothing too fancy. When we want to see what's happening, explain is a great tool. I've used this very long explain output and I've ended it with format JSON. And that's so I can use this PG Mustard website that is available now to help analyze our analyze plans. So I'm going to flip over here, and there's a URL right in the SQL script that has the publicly shared version of this. Um, I just wanted to run that so I can show that all you have to do is run it in format JSON right here in dbeaver. You can copy it, and then in PG Mustard you can just paste it right in, and it does all the parsing for you. What I really like about PG Mustard is it tries to give helpful suggestions in a friendly way with context and resources. These are all very important details, especially for folks that are a little bit intimidated by running explain analyze and looking through all of that nasty output. Until you get a taste for it and a feel for that, if you don't do it all the time, it can be a little rough. So this is a really helpful tool for sort of taking away some of that complexity and some of the dauntingness of it. So the first suggestion it says is count can be inefficient. Well, yeah, I know that. And I want to do a count. So I'm going to ignore that first one. I'm going to click on this second one, this row estimate. This is something I care about. I don't like bad row estimates. If you have bad row estimates in Postgres, it's going to likely give you a bad query plan and it's not going to perform at its peak. Here we can see the row estimate is out by 147, a factor of 147. And if we fly out this tab, it gives us a little more detail that it expected 82 rows for each iteration of this loop, but it actually produced 12,000 rows per loop. This is a major, major issue when you have row estimates that are off by this far. This is the kind of thing that causes just-in-time processing to kick in when it's not appropriate. So this is bad, and this is one of those side effects. It's common with PostGIS queries when you're using like an st-intersects or something like that. Bad row estimates are unfortunately common, and they're getting less and less common and less severe, but they do happen. We have a tool to help with this, and it's st-subdivide. Inside of the data processed here, we have a view, vplace polygon subdivide, that all it does is subdivide the polygons from vplace. So we have our unduplicated cleaned place polygon with the names from getName, and then now we also have this, the extra layer of geometry to join to. So I'm going to join between the place itself and the subdivided polygons, and I do that because I want this filter here. And I also want the name here, and I haven't included those columns in the subdivided view. But once I've joined to the subdivided view, st-intersects gets replaced with that geometry instead of the base place geometry. So it'll use the subdivided geometries. And what this does is it gives us smaller pieces. Each comparison that Postgres does can look at a smaller piece of the pie. So if I take and copy and paste this plan, into the browser so we can see this, we now see our row estimate is only out by a factor of 22 instead of 147. It's not perfect. I wish it was still better, but it's not. But it's still a whole lot better than the original with the full glory of the polygons without the subdivide. And if we look at the timings here, the total time on the one with the full polygon was over 4 seconds, and the one with subdivided polygons, just over 2 seconds. So it runs about twice as fast. And largely a big part of that is going to be that the row estimate was not as far off, and so it gets a better plan for the query. All right, place polygons. Same thing happens with trees. This is the same basic kind of query. We're joining a big polygon and we're looking for points inside of it. Here I'm using st-contains instead of st-intersects and filtering for trees. If I run this, I'm going to run this a couple times just to make sure that all the data is in buffers. And if you're looking at this bottom execution time, 400, 500, 600 milliseconds. if I rewrite the query, join to subdivide, and then use that for the st contains and run this again, I'll run it a few times to be fair. 150, 175 milliseconds. Again, it's about twice as fast as the one using the full size of the polygon. And so this was one of those, the subdivided polygon, it was one of those details that everybody kind of needs all the time. So I baked that in here. I believe that's a materialized view with an index. Let's go look. Materialized view. Yep. vPlace polygon and vPlace polygon subdivide are both materialized views, and it should have an index on the gist index. Yep. So we should always get good spatial performance here. All right. Continuing on with places, but another frame of reference on places. This was an interesting request that came in. I was talking with some folks on Slack, or one person in particular on Slack, the Postgres Slack channel. And he is having a problem with this type of data. And he shared some queries with me, and I asked him if he minded if I wrapped this up into this project, and he's like, oh, please do it. So this is based off of some code I got from someone else. And it really is way cool. I never would have thought that this was so exciting, but it has a number of really neat benefits. And I see there's a question about PG mustard. I will come back to that here in just a minute. The nested polygons allows us to find this place within that place. Again, using Golden, I can see here that Golden is inside Jefferson County, which I happen to know it is. It gives us a nest level. So this is telling us how many polygons are in this chain of polygons. There's the ID for this row, and then the path of the IDs. So this gives us the ID of every row contained in the name path over here. Same with admin level paths, so we can kind of trace what admin levels we had. And then there's this innermost flag. This is another Boolean true false. And this really just says this particular polygon does not contain another admin polygon. It's the innermost admin level. And this has turned out to be kind of a neat little indicator to play with. The nesting levels that you get are determined on the size of the region you've loaded. So if you've only, in this case, I've loaded Colorado, OSM_CO has Colorado. It curiously does not have Colorado in the name path. Golden is certainly inside of Colorado, but it turns out that the geofabric region, subregion of Colorado does not contain the Colorado polygon itself. Probably because it lines right up on top of the boundary that they're using, so it doesn't get included. But it's just one of those odd, I didn't quite expect it, but it makes sense when you think about it sort of things. So if you load a larger region, so here, same basic query, I'm just looking at US West instead. Now we get a path with one more detail in it. We have Golden, which is inside Jefferson County, which is inside Colorado. So that is good. And so if you loaded North America, you'd get Golden inside of Jeffco, inside of Colorado, inside of North America. If you create a planet Earth polygon, you could even get planet Earth if you wanted, I think. That'd be a little tricky, but. And here we can see the nest level is now 3 instead of 2 because it includes Colorado as well. And now we have the admin level path is 864. Awesome. So another way, it's neat to look at one row. This data comes in more handy if we write a query like this. The filter is saying, give me everywhere that has Jefferson County that intersects with this name path. And so this name path is an array. So we can use this kind of syntax and compare arrays against arrays. If I wanted to add a second county in here, I could say, let's also include Adams County. So I could update queries like that fairly easy, like it was as if it was an in clause. So I want Jefferson County, and I also want it to be Jefferson County, Colorado, because there are other Jefferson counties in the world. And then I also want to exclude Jefferson County itself. So I'm saying I want all of the admin polygons within Jefferson County of Colorado, but not Jefferson County itself. And it runs super, super fast. If I run this with the explain analyze, we can see zero 0.2 milliseconds, sub-millisecond performance on this kind of query. This is because we've pre-processed all of this nesting level and we have these indexes on these simple text columns instead of trying to do the really complex spatial analysis. So this place polygon nested table has all of this nesting detail that allows us to write some really, really nifty queries that otherwise would not be possible. This nesting is far from perfect. I've already fixed a couple oddities. There continue to be oddities. And the more I look at this, I'm starting to be suspicious that it's as much of a problem in the tags in OSM and the way the data is structured in OSM as it is my code. So there probably are bugs in my code and my logic. This is a pretty complex thing, set of queries that generates all this. But here we see we have two different Arvadas of admin level 8. Somehow one of them doesn't have any parents. This Arvada just is an orphan apparently. Then there's an Arvada within Jefferson. So there's some weird things going on. Jefferson County or Lakewood, also in Jefferson County, has some oddities as well. I plan on looking into these. I'm not sure how perfect we can get it and how much is a limitation of the quality of the OpenStreetMap data itself. Haven't quite made that determination yet. It looks like there's been a couple questions come through. Lindsay, do we have anything new?
What we have is the question about PG Mustard.
Okay.
Where do you copy the plan to PG Mustard?
Perfect.
And then we have some chatter around that.
All right. So I'll just go through that again real quick. So you have to run it with format JSON. That's the big thing, is running explain analyze with format JSON, and it'll give you this JSON mess. I don't know how else to say it. It's a mess of JSON. You can look at it here on the panel if you want. But just click inside the cell of that plan and Control-C to copy. And then over here in PG Mustard, there's a new plan button. Oops. And my Zoom stuff is in the way. And that has a window like this. And so it's just a matter of pasting this plan inside the window. And it's just all there. And then submit, and it processes it. And this is a relatively new tool compared to some of the other, like the Depez site. I really like Depez's explain tool. There's a few others that I like. As I said, this one is really handy because of the advice it tries to give and the resources. It provides links to documentation and other things that come in handy. So that's how you go through that. And the PG Mustard folks, Michael is who I've been talking to, have been incredibly helpful and responsive to feedback. So if you have any feedback, I recommend getting in touch with them and letting them know. All right, so go back down to where I was. Okay, so now this is another query, kind of like the I want to ride my bike, but I can't walk here kind of query. This is another query that just wasn't possible before. Here, I'm looking at the innermost places from Colorado and Utah. So I want admin polygons that are at the lowest level within these two states. And so I can run this query and I can see, looking at this admin level, we see 8 and 99. Experienced OSM folks might be going, 99, what? Well, that's the, as the comment will say, if there's no admin level, I throw in a default of 99. That allows me to sort things and not miss out on things that otherwise don't get an admin level set. So there's that in there. But if I flip over to the spatial tab so we can see the data in spatial format and zoom in, we see that we have a lot of little polygons around Colorado and Utah. We have the innermost polygons from these two states. And I don't know how to get this kind of query from the raw data. Here in a second, I'll show my best attempt. It's not perfect. On the topic of not perfect, I would expect to see Aurora here and Westminster and Broomfield and Louisville, like all these places that don't have polygons. In this nesting, I'm pretty sure it's because they don't perfectly fit inside other polygons. But again, I haven't fully worked out the kinks on this, but the reality is this type of query is cool enough that I don't care. It's OSM data. There's always going to be the caveat that it's not perfect. Um, and the best that I can do without this innermost and this nesting is a query like this. So I have my place polygon and I'm joining to my place polygon where it contains itself. So I can write one of these queries. And this will work running it with the explain analyze. Row count, 4,500 rows get returned from this. Let me switch over to text so you can see that a little better. 4,500 rows returned from this simple version, and it took a quarter of a second roughly to return. Not terrible, but if we compare it to this query where it doesn't have to do anything with PostGIS, oops, and I run it with explain analyze, not returning data, this one returns in 1.2 milliseconds instead of a quarter of a second, and it only returns 657 rows instead of 4,500 because I don't have a way to get to this innermost flag of that nesting data in this kind of thing. You have to go through a whole series of really complex spatial steps in order to do that in this kind of query, and then your performance can tank. So this is another just, wow, I can write queries I never could write before. Get so excited about the craziest things. If you know the OSM ID, so if I wanted to find all the places in Colorado, I can do the same kind of thing, but instead of using the name path, I can use the OSM ID path. So here it's saying, find me all of the places inside Colorado. If I run this without the explain analyze, and oops, I don't have the geom column in there. That would help if I want to display the results. And that's why I didn't want to include these results. It takes a little while. There we go. So this kind of query will return all of the place polygons within the Colorado boundary. So we have, it's limited at 200 rows right now, but you can see the wide array, vast array of sizes between the counties and the local places. All right, moving on to addresses. Addresses and other details. This is one of those little things that I occasionally need. I don't need it a lot, but I need it often enough that I went ahead and added in a generated column to concat all of the address parts together. And I see there's an extra comma here after the city name, so I probably need to fix that coalesce statement to not do that. But this is just kind of a simple, oh, nicety. I like that. I don't have to go through and pull all these different parts together and deal with nulls at runtime. But we have, in this case, I'm querying the shop point table. One of the things in OpenStreetMap is there's also polygons. We have shop points and we have shop polygons. There's a few other layers that have this pattern. And so there's an underscore all version. The underscore all version takes the data from both tables and the polygons get turned into points using stcentroid. So this way, and there's a geom type column here to indicate whether it was an N for a node or a point, or the W indicates that it came from the polygon. And so in this way, we can get all of our shops in one view with a consistent geometry type for styling. So I'm not a big fan of mixing points, lines, and polygons into a single result set. That gets messy. Using the data dictionary view for views, we can see that there are currently 3 different underscore all views that combine these layers together. So we have the shops that we just looked at. There's buildings. I use that one quite frequently as well. And then the POI, or points of interest. This is one of the newest layers in the project, is the point of interest layer. So this allows you to look at the same kind of data all in one place without having to worry about what type of geometry it is. Looking a little bit at points of interest, we have a handful of different tags that get brought into here. So we've got amenity, we've got tourism, and natural and land use. sometimes when you see the name of tags in the OSM type column, you'll also find an OSM subtype column. So if you're like, okay, what does Ryan consider to be a natural point of interest? Well, peaks, glaciers, hot springs, and bay are pretty much what I lumped into there. And I'm just kind of going through a couple little laundry list things as we get to the end here. The tags table, this runs with run all and is excluded if you use run no tags. One of the really handy things in here is if I'm looking for something specific, I'm looking for Pangea coffee roasters, and I want to see what all of it looks like in OSM. This tags table has an OSM URL that you can just click on from dbeaver, and it'll poof open up in your browser and select that item in OSM. So I could look through all of the raw tag data here in OSM, go back to my dbeaver window and go, okay, now why do I not see what I expected here? And of course, there's this tags column. That's where I'm filtering this name. This is the JSON-B column. If I were to run that here, add that in, we could see at the end we have just this open-ended key value, oops, data in the JSON column with all of the information. And then the unit table, this table is here for debugging purposes only. It smashes everything into one big table, geom type, OSM ID, JSON column with all of the data and the geometry. So we can see line, string, and point. Just after I said I don't like doing this, there are times where this is handy, mainly when I'm working on figuring out why something didn't show up. This gives me a way to say, oh, okay, I see it here. Is very handy, but do not use this for production. If you submit a bug that you have bad performance and you're using the unit table, I will close it immediately. Not messing around. So with getting through all that SQL code, quick promo. I have been writing a book for way too long now. I am in the final editing stages and working out legal publishing details and hope to have it published this summer, hopefully before July. So feel free to check that out, postgis-osm.com. There's a place for you to put in your email if you want to sign up for updates and be notified when it is actually published. There's some resources here, links to the PgOSM-Flex project and OSM to PGSQL. I will update the page that has the downloads to also include all of the links that I've shown today, so that all of those links will be there for easy access in the next day or two. All right, any other questions?
You are currently caught up, but let's give everyone one more moment to get your questions in. And in the meantime, I'd just like to say thank you so much, Ryan. This was fantastic.
Thank you. It's been a lot of fun. We waited about a year since the last one of these, which was a little too long. I was itching for doing one of these. So thank you for hosting it again. And I do see the dbeaver was the tool, the GUI tool that I was running all the queries in. I really like the spatial viewer. One thing, I'm just going to show this real fast, get up to where I've got a geometry. There are some really nice things with dbeaver and the geometry viewer. If you select a single row and fly out the panel on the side, you can look at that geometry independently of all of them. Or you can see everything that's in the data viewer by clicking over the spatial tab. On this spatial tab, it handles a good number of SRIDs. I'm using 3857. It defaults to your base OpenStreetMap, but there's this little drop down right here. And one of the ones I really like using is OpenTopomap, is to give you a different base layer. And so then you get your data overlaid a completely different base layer. And there's even the, I believe one of the newest version which I'm not on right now, has the ability to add your own custom base layers. So there's a lot of really neat things happening in dbeaver around the spatial viewer. Excellent. Yeah, so the whole country, don't try to use this Docker image. I highly recommend installing it on, setting up a server. At least 64 gig of RAM, as much RAM as you can afford to throw at it, honestly, to get it in. It's a big, big data set, but at least 64 gigabytes. Make sure you use flat nodes for so it doesn't have to use at RAM as much. And don't start by testing the whole world or even like North America. Start with a small region. I love getting using the DC area just to get familiar. It feels really lightweight and it's easy, but it allows you to practice the steps without, a multi-hour turnaround to find the error. So if you're doing something wrong, it doesn't always break right away. It'll break halfway through the process. And North America or Europe or any large region is going to take a few hours to run. So I recommend starting small and scaling up on a dedicated server for the process. And as far as data source, GeoFabric is my go-to. There are other ways to get OSM data in the PBF format, but I've used GeoFabric for my downloads for basically a decade, and I have no reason to switch personally.
Well, fantastic. Ryan, thank you again, as always. Thank you to everyone who joined us today. Thanks for your questions, and I hope to see you on future Postgres conference webinars. Cheers.